Hey, chemistry. I want to show you a little trick with the periodic table today that will help you write electron configurations. Now, the periodic table is this marvelous tool that's packed full of information, and it's really useful if you just know how to use it. We're going to get more into that a little bit later as we unpack the periodic table. But for now, I want to show you one of the cool things about the periodic table and how it can help you. So, in order to show you this tool, I need to first show you how the periodic table is related to electron configurations. So stay with me for a couple minutes. Basically, what I want to do is go through the periodic table and show you the electron configurations for each element. And in doing so, there's going to be a pattern that emerges that's going to be a really helpful pattern for you. Okay, so we're just going to start by writing a couple electron configurations. So the first one I'm going to write is hydrogen, and hydrogen is 1s. Oh, that's an excellent start. 1s1. Okay, so in the box on the periodic table that belongs to hydrogen, I'm going to write its electron configuration. Okay, now helium is similar. It's 1s2. So in the helium's box, I'm going to write 1s2. All right, lithium is next. So lithium is going to be the same as helium, only 1s2. It has 3 electrons, so the third electron goes into 2s1. 2s1. All right, and we're just going to keep going across the periodic table like that. Beryllium has 4 electrons, 1s2, 2s2. Boron is next, 1s2, 2s2, 2p1. All right, carbon, 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. Oxygen comes next, 1s2, 2s2, 2p4. Fluorine comes next, 1s2, 2s2, 2p5. And then we get to neon, 1s2, 2s2, 2p6. Okay, so do you kind of see what I'm doing? I'm writing out the electron configuration, and then I'm just taking the very last suborbital that I write of each of them, the very last one, and then I'm putting that into the periodic table. So rather than watch me do this, why don't you guys go ahead and fill in the next 2 rows of the periodic table like this. So pause the video here, fill in the next 2 rows of the periodic table with the ending suborbital of the electron configuration, and then let's compare what we come up with. Okay, so if we work through the whole first 4 rows, we're going to see something that comes up like this. And there's a couple patterns that emerge. Now would be a good time to pause the video again and see if you can list out a couple of those patterns. Pause it here and tell me about a pattern that you see. Okay, so one of the patterns that you should start to see is that blocks start to emerge. And if we kept going down the periodic table, these blocks would stay very consistent and just get more evident. So this block right here contains the very last electron is always put into the same shape. It's always put into the S shape. And so we call this the S block. Over on the other side, this block right here, the very last electron also always goes into the same shape. And that shape is P. So this we call the P block. Now notice helium's kind of hanging out there in this case all by itself. Helium in terms of blocks really does belong with the S block. But there are other reasons that we really haven't talked about yet why helium should be classified where it is. And so for now, we just assume, like when we're talking about blocks, helium is part of the S block. It's just not over there right now. Okay. You see a block in the middle here. The very last electron to go into a shape along this whole row is the D block. And then I bet you can guess what these might contain down here. And if you said they are the F block, you would be right. So we start to see blocks emerge in a very consistent pattern. Now, like we talked about just a second ago, helium doesn't fit this pattern very well. And so we can conclude that the periodic table was not organized off of these blocks. And in fact, at the time when the organization of the periodic table was decided on and come up with and agreed upon, the quantum mechanical model was not even in discussion yet. And so the periodic table was not organized off of blocks. It's just one of the beautiful patterns, one of the really useful tools that came out of the periodic table when it was organized like it is. All right. But the fun doesn't stop here. There are more patterns to be seen. So besides blocks, let me point out a couple other things to you. Notice that when we talk about rows, so in a periodic table, a row is called a period. So true chemists are not going to talk about rows on the periodic table. They're going to talk about periods on the periodic table. And each period on the periodic table, notice they line up with the number of the row that exists. So the first row is the first period. The second row is the second period, and so on and so forth. And if we were to continue down the periodic table, the pattern would continue as well. And these periods, notice, they line up with the energy level. So we can pick a random element off the periodic table, and I can tell you exactly which energy level its last electron is going to go into. This one, for example, since it's in the 1, 2, 3, 4, 5, 6th row, or 6th period, that very last electron that is going to fill into this atom is going to go into the 6th energy level. So each row or period is going to correspond with the energy level of the valence electron, of the outermost electron. Likewise, if you look at let's go orange. If you look at the columns, columns on the periodic table are also, they also have a special name. They are called families or groups. You'll hear both terms used. So notice each family or each group has a very consistent last electron. That very last electron that goes into each family always goes into the same shape, and there's the same number of electrons in that shape. So for example, this family or this group, its very last electron will always be the fourth electron in the p orbital. And what's more, okay, hold on. Before I tell you what's more, let me just show you that this is always consistent. So we can look at the first row over here. They all have that very last electron going into the s orbital, and it's always the first one in the s orbital. We can even pick something out of the d block, and it's going to be consistent as well. If we were to finish this periodic table off, you would notice that all of these are going to go into, be the third electron going into the d orbital. The only thing that changes is which d orbital it's going to go into, the 3d, the 4d, the 5d, the 6d orbital. What's more, if you count over and skip this d block here, we count over 1, 2, 3, 4, 5, 6, 7, 8. Notice, we'll go back to this family right here. This is the 6th column, and there are 6 electrons in that outermost energy level. If we look at this element right here, notice you're in the second energy level, and there's 1, 2, 3, 4, 5, 6 electrons in that energy level. 2 in the S's and 4 in the P's. 2 plus 4 is 6. So yet another pattern is emerging. Okay, so all of this is very helpful when you're writing electron configurations, and I'll show you that in just a second. But I do want you to notice just one thing more. Notice that while the S's and the P's, the S block and the P block, line up beautifully with the energy level or the period number, notice in the second row, you have the 2 S's and you have the 2 P's, right? That lines up really nicely. Well, look at the D's. The D's start in period 4. So in period 4, you have 4S, you have 4P, but notice you do not have 4D. So the D's are offset by 1. So in the 4th energy level, you're not going to find 4D, you're going to find 3D. In the 5th energy level, you're not going to find 5D, you're going to find 4D. So the D's are offset by 1, the F's are offset by 2. So down here, this F, the very first one, we know we're going to have the F shape. We know we're going to have 1 electron in that F shape, but those F's should go right here. And so this is going to start on the 6th energy level, or the 6th period, but the F's are offset by 2. So this isn't going to be 6F. It's going to be 4F. It's offset by 2. So that is something you have to know. In order to use this tool, you do have to know all the blocks, S, P, D, F. You also have to know that the D's are offset by 1, the F's are offset by 2. And you can prove this to yourself if you just keep filling out this periodic table all the way, like we have been. Fill it out completely, and you'll see that the pattern continues all the way into the F block. Now, here's the beauty of this. Let me show you why this is going to be helpful to you. This is helpful because if you know the blocks, you know the D's are offset by 1, you know the F's are offset by 2, and you also know that the row numbers or the period numbers line up with the energy levels, then you can use this instead of the Aufbau principle to write your electron configurations. Let me show you how. Okay, so we're going to pick one. Let's choose fluorine, for example. Okay, so fluorine's over here. I'm circling it in purple. Fluorine is going to be this number. So instead of following along with the Aufbau principle, I'm going to use this periodic table. So for fluorine, I'm just going to count over until I get to the fluorine box. Okay, so here's electron number 1. It's in the first row. It's in the S block, and I have 1, 2 of them. And then I'm going to have 1, 2 electrons in the 2S block. And then in 2P, I'm going to have 1, 2, 3, 4, 5. So I just wrote an electron configuration by reading from left to right, top to bottom on the periodic table. Let me show you another one. I'm going to show you zinc. So zinc is right here on the periodic table. Okay, but instead of using the periodic table with all of this written in it, I'm just going to use a blank periodic table. So I'm going to delete all of this. For your sake of following along and seeing how this is done, I'm going to circle all of these blocks again, just so it's easier to see when we come across a block. So there's the S, there's the P, I think D I had in pink maybe. All right, and then the F I had in green. Okay, so we were going to do zinc. So zinc is right here on the periodic table. So I'm just going to read left to right, top to bottom on the periodic table until I get to zinc. Okay, so zinc's electron configuration. So I'm going to be in the 1s block. So 1s, and there's 2 electrons there. And then here I am in the 2s block. 1, 2 electrons there. Then I'm in the 2p. I'm still in the second energy level, but now I'm in the p block. So 1, 2, 3, 4, 5, 6. Okay, now I'm here. 1, 2, that's the 3s. And now I keep going over left to right. Now I'm in the 3p block, and there's going to be 1, 2, 3, 4, 5, 6. All right. Now I'm in the 4s block. So 4s, there's 2 there. Now here I'm in the 3d. Remember, the d's are offset by 1. So I am in the 4th row, but d's are offset by 1. So this is going to be 3d. So 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d, 10. Chana. There is my electron configuration. Okay, now it's really, really helpful to do this with the noble gas configuration. Let me erase this and start over again. So we can do zinc again. Zinc is right here. So I'm going to go to the last noble gas that I've passed. I don't want to go to this noble gas right here, because that noble gas has too many electrons. It has more. I have to add electrons to get to that noble gas, right? So I don't want to go there. I want to go backwards to the noble gas before it. So I'm going to start there at that noble gas. Let's go look at a real periodic table and figure out what that noble gas is. Okay, here we go. So I'm trying to get to zinc. Oops, let me choose a color here. Come on, let me choose a color. All right, zinc is here. So I'm going to go to the last noble gas, which is argon. So for zinc's electron configuration, I'm going to put argon in brackets and then just start counting. So this is my first electron here on the K, and this is in what energy level? 1, 2, 3, 4. It's in the 4th energy level. S block, and there's 1, 2 of those. Now here for scandium, I'm in the 3D block. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there is the noble gas electron configuration for zinc. And I can do this for anything. I can choose something crazy from the bottom. Let me go all the way down. Let's do like, I don't know, EU. Oh, I picked blue. That was probably not the best choice. Let me pick a different color so you can see it a little bit better. Okay, EU down here. We're going to do the electron configuration for EU. So EU, I go to the very last. So remember, this whole shebang down here should fit right here. It's like they cut the periodic table and took a big chunk out of the middle and squished the periodic table back together. So EU is going to come out of this 6th row. So I'm going to go to the last noble gas, which is xenon, and then count over. So this is these two right here are in the 1, 2, 3, 4, 5, 6th energy level. So 6s, 2. And then I hit the F block next. So this should be 4F. 1, 2, 3, 4, 5, 6, 7. 4F7. And there's a noble gas configuration. So noble gas configurations are so much shorter. And when you are using this periodic table shortcut, instead of using the slashy line Aufbau diagram, right, it becomes really simple. But you must know the blocks. You must know that D and F are offset, D by 1, F's by 2. And then you have to know that each period or row in the periodic table corresponds to the energy level. And if you know those things, then writing electron configurations becomes so simple just by understanding the tool that the periodic table is and being able to use it. So try this with your homework tonight, and we can talk about it in class tomorrow. Let me know if you have questions. See you in class.